All right, let's dive straight into your rapid revision for AQA GCSE Physics. We're tackling space physics today. That's section 4.8.1. We're going to cover the absolute essentials you need to know to absolutely nail this in your exam. So let's get right to it.
So have you ever looked up at the night sky and wondered about the big stuff? How does a star even begin? What happens when it dies? And what is this invisible force that's keeping us locked in a perfect loop around our own star? Well, these are the massive questions that your syllabus wants you to answer.
Here's our game plan. First, we'll get our feet on the ground in our own solar system. Then, we'll get into the incredible life story of a star, from beginning to end. After that, we'll look at the force that holds the entire universe together, gravity. And to finish, we'll lock it all down with a final checklist of the key facts you just have to know. Okay, first things first, let's start with our own cosmic backyard and figure out how it all began.
So what exactly is a solar system? Well, the key definition you need is this. It's a star and everything that's gravitationally stuck to it. For us, that's our sun, the 8 planets, and all their moons. But, and this is super important for context, you have to remember that our entire solar system is just a tiny, tiny speck inside our home galaxy, the Milky Way.
So, how did our sun even get here? It all kicks off with something called a nebula. Just picture a gigantic cloud of dust and gas floating in space. Then gravity, the hero of this story, starts to work its magic, pulling all that stuff together. As it all collapses inward, it gets hotter and denser and forms what we call a protostar. And when the pressure and temperature in the core get ridiculously high, boom! Nuclear fusion kicks in and a star is officially born.
Now, this leads to a really crucial idea. For billions of years, a star like our sun is in this perfect state of balance. You've got gravity, which is constantly trying to crush the star inwards. But at the same time, you've got this colossal energy from fusion pushing outwards. It's like a cosmic tug of war, and as long as those two forces are perfectly matched, you have a stable, main sequence star.
So a star is born, but what happens next? Its entire life story, from that stable middle age right to its death, all comes down to one single factor: its mass, how big it is. Let's start with a star about the size of our sun. Its life path is, well, relatively calm. After billions of years as a main sequence star, it starts to run out of fuel. It'll swell up into what's called a red giant, then it sheds its outer layers, leaving behind this super hot, dense little core called a white dwarf. And then, over an almost unimaginable amount of time, it just cools down and fades into a black dwarf. But what if the star is huge? We're talking way bigger than our sun. Well, their ending is anything but calm. It's spectacular. They swell into red supergiants, and then they collapse and explode in a supernova, one of the most violent events in the entire universe. And what's left behind is just as extreme, either a crazy dense neutron star, or, if the star was a real giant, a black hole. And this is why supernovas are such a massive deal. They're like the universe's ultimate factories. The unbelievable energy in that explosion is the only thing in the cosmos powerful enough to create elements that are heavier than iron. Just think about that. The gold in your jewelry, the calcium in your bones, every single one of those atoms was made in the heart of an exploding star, billions of years ago. Okay, final section before our checklist. We've talked about stars, but what keeps planets and moons and all that from just flying off into deep space? Once again, it all comes down to our old friend, gravity. So here's the absolute fundamental principle you have to remember. The force that keeps everything in orbit is gravity. It's that constant pull between the Earth and the Sun, for example, that provides the perfect force to keep us moving in a stable circular path. And this rule applies to everything, big or small. Planets orbiting the Sun, gravity. Our moon orbiting the Earth, gravity. All those thousands of artificial satellites we use for GPS and TV, you guessed it, gravity. They're all essentially in a constant state of falling sideways around a bigger object, held perfectly in place by its gravitational pull. Okay, higher tier students, listen up, because this is a classic exam trap. For an object in a stable circular orbit, its speed is constant. It's ticking along at the same rate, but its velocity is constantly changing. Why? Because velocity has direction, and in a circle, your direction is changing every single second. Speed is constant, velocity is not. Don't mix those two up. And one more for higher tier.
For an orbit to stay stable, speed and distance are completely linked. If a satellite speeds up, it has to move into a bigger, wider orbit to stay stable. If it slows down, it'll drop into a lower, tighter orbit. You can't change one without changing the other. All right, you've done the heavy lifting. Now let's boil it all down and lock in the most important points with a final checklist. This is what the examiners really want to see that you know.
Okay, 4 key takeaways. Number 1, you've got to be able to explain how a star is born. Remember the steps. A nebula collapses under gravity, it forms a protostar, and then, boom, nuclear fusion begins.
Second, you need to know the 2 different life paths for stars. Remember, sun-sized stars end their days pretty quietly as white dwarfs, while the massive stars go out with a bang, a supernova. And that brings us to number 3. Those supernovae are the cosmic forges that create every element heavier than iron. And finally, number 4, gravity. It's the fundamental force that provides the pull needed to keep everything, from planets to satellites, locked in a stable orbit.
And just one last reminder for all you higher tier students, a constant speed in a circle means a constantly changing velocity. Got it? Good. Don't get caught out. And just to finish, here's a thought to take with you. Your course touches on the Big Bang Theory, our best explanation for how the universe began. But science is never done. Right now, the biggest questions in physics are about dark matter and dark energy, this mysterious stuff that makes up about 95% of the universe, but that we can't see or explain. What could it be? Well, that's a question for the next generation of physicists to answer. Good luck with your revision.